Due to its molten iron core, the Earth has a magnetic field around it, just like a bar magnet. This magnetic field extends outwards into space, forming a big bubble that we call the magnetosphere. The inner layer of the magnetosphere, from near the Earth's surface up to 1,000 or so kilometers, is called the ionosphere because it is made up of particles ionized via radiation from the sun. In low-frequency radio astronomy, when we point our telescopes to the sky to measure the faint signals that travel through space to reach us, we need to take structures and perturbations in the ionosphere into account that might change these signals. We need a good understanding of the effects of the ionosphere to make sense of our data. Pictured near the surface, the Earth's magnetic field lines run parallel and come out at an angle to the ground. It has long been postulated that tubular plasma structures go along the magnetic field lines, and it is structures like these that can affect our astronomical measurements. Previously, people could only guess what they might look like, since no one has ever been able to image them. My name is Cleo Loy, and I am an astrophysics student with Castro at the University of Sydney. I have found that we can use a new type of radio telescope to not only detect these plasma tubes in the ionosphere, but to actually image them. And what's more, we can reconstruct their behavior in real time and in 3D. This is a very exciting world's first. The Murchison Wide Field Array, or MWA for short, is a radio telescope in the Western Australian desert. It consists of 128 receiver tiles, spread over a circular area roughly 3 kilometers across, that work together as one instrument. What makes it so special is its huge field of view, letting us observe a large patch of sky and all sorts of celestial objects as they flash or pass overhead. We use the MWA to study how the ionosphere shifts around the observed positions of objects in the sky and distorts them. A good analogy for this is the way lights at the bottom of a swimming pool dance around when the water ripples. We cannot see the water directly because it is transparent, but from the dancing lights we can determine the pattern of the ripples at its surface. Just like when we are looking at an angle down parallel train tracks, if you were standing at the site of the MWA, the Earth's magnetic field lines would appear to converge. What we saw with the MWA was a stunning distortion pattern that strongly coincided with the magnetic field lines. For the first time, we revealed the true nature of these structures as a vast array of plasma tubes, filling the sky in staggering numbers. The MWA's rapid snapshot capabilities allow us to make movies showing their motions over time. But that's not all. The MWA also has the power to see in 3D. When we look at an object, our brain combines the images from our two eyes, allowing us to judge how far away it is. So by analyzing the signals recorded by MWA tiles in the east, separate to tiles in the west, we give the MWA the ability to perceive depth. This has never been done with a radio telescope before. By using the MWA like a pair of eyes, the three-dimensional nature of the tubes springs into reality. We can measure their heights above the ground, see their steep inclination, and watch as they drift sideways towards or away from the MWA. This is a whole new way of looking at the sky.
It's called the ambipolar field, and it's an agent of chaos. It's an electrical field. It begins at about 250 kilometers above your head, and it keeps going. The atmosphere up there is different than the atmosphere down here. Thinner, right? There's less of it. So think about just one atom. Here it is. The sun shines on it, it breaks off this electron. So now we have this negatively charged electron and this positively charged ion, and the two are attracted towards each other. The electron would happily escape all by itself, but the ion still feels the big tug of gravity. So as the electron tries to pull away, the electric force forms between the two to restrain it, to keep it from escaping. And it also helps pull the ion upwards. The field works in both directions. It is ambipolar. Imagine you're walking a dog, and you've got a tiny, tiny little dog, and it's pulling on a leash. That dog's going nowhere. This ion and electron pair that you've been thinking about, they are only one in an enormous sea of the ionosphere. But overall, because gravity's pulling down on the ions, it adds up. And over a large distance, you get this field forming. It's like this conveyor belt that's countering gravity and lifting the ions up so they can escape to space, which is why it may have had an impact on the evolution of the atmosphere.
3, 2, 1! Ignition! Nothing goes!
During the 15-minute suborbital flight, we successfully measured this ambipolar field for the first time. When you add up all of the strength of it over the whole flight, the whole potential drop was only about half a volt. And that's nothing, right? That's about as strong as one of those tiny little watch batteries. But that's exactly the amount that you need to explain this, polar wind escape, this outflow. Because we measured it for the first time, we can actually understand the role it plays in the atmosphere. And despite being weak, it's incredibly important. It counters gravity and it basically lifts the skies up. It's like this conveyor belt that's lifting this atmosphere up into space.
So if you forget everything else I say tonight, the one thing to remember here is that Earth's atmosphere is always electrified. Normally, we just think about charge when there's thunderstorms and lightning around, but it's electrified all the time, and charge is continuously generated. And that's through a process called ionization. So positive and negative charge is created by ionization all the time. And in our atmosphere, there are two sources of ionization. The first is from galactic cosmic rays. So these are highly energetic particles from basically outer space, from outside our solar system, and they enter Earth's atmosphere from above. And as they do so, they create a cascade of charged particles right down to the surface. And because they come from outside our solar system, they're modulated by solar activity. So they respond to magnetic fields. The other source of ionization is radioactivity at the Earth's surface. So this is mostly from gamma radiation from the soil. And so this emits ions, which can be transported upwards, but they're typically trapped in the boundary layer. So they're stuck in the lowest kilometer of the atmosphere. We're looking at this. So how do these clouds become charged? Well, to do that, we have to think about some of these atmospheric electricity parameters a bit more. So we have to consider what's called conductivity. So conductivity is the ability of the air for a current to flow in the air. And it depends on this ionization from our cosmic rays and from our radioactivity. So these tiny little ions that are created in a cloud, they become attached to the droplets. And that means that the conductivity goes down when you have a cloud layer. So this is our cloud layer. We're going up through a cloud layer. So our conductivity decreases, is low in the cloud, and it increases when we get above the cloud. If we go to Ohm's law, which if you remember back to your school days, you probably did this in the form of V equals IR. It's basically the same equation, just written in a different way. And that says if you have a current, so in this case, JC, it's flowing through the cloud, and you have a conductivity or resistance, basically the inverse, then if you have an electric field, then the conductivity and the electric field are inversely related if the current stays the same. So because we have a conductivity decrease, we must have an electric field increase in the cloud. And if we take another relatively simple law of electrostatics, so Poisson's equation, that says if you have a gradient in electric field, then you will create a charge, a space charge, rho. So you see that there's a gradient in the electric field on the bottom edge of the cloud and on the top edge of the cloud. So that means that we should get a charge, rho. And that's what we see here. So this is our charge density. So because of the direction of the field and the current flow, we should get negative charge at the base of the cloud and positive charge at the top. And if we manipulate these equations a little bit more, this charge depends on a few things. It depends on the conduction current, so our JC, which depends on the global circuit and therefore the thunderstorms. It depends on the conductivity, which depends on the ionization from the cosmic rays. It depends on the gradient of the conductivity, which is this bit here, which depends on the height of the cloud, but also the cloud droplet properties. So if we have a really sharp cloud edge, we should see more charge than if we have a woolly one, if you like. So that's what theory predicts. So our theory predicts that cloud edges are charged and that the charge should be transferred to the cloud droplets. So what does this charging of droplets do? Well, we'll discuss this in a bit more detail shortly, but basically it affects the microphysical interactions between aerosol particles and droplets. And collisions and coalescence, which is something that's particularly important in clouds, is affected by charge. So this means that things like the lifetime of the droplets, how long they last, and how they grow can be affected by charge. And many of you will know that it's these small-scale cloud microphysical processes that determine the large-scale properties of the cloud, such as the height of the cloud, its opacity, or how much its reflectivity, basically, how long the cloud lasts, and even the rainfall.
Everything in the universe sends out radio waves: planets, nebulas, comets, pulsars. These radio waves, which are invisible to the eye, are sent out in every direction and can travel billions of light years to eventually reach Earth, although the signal has weakened quite a bit by then. Here, they can be detected by radio telescopes, such as the International LOFAR telescope, which spans several countries. Each LOFAR station consists of many antennas. These different antennas catch the radio waves and send them to a central receiver, which converts the analog radio waves into a digital signal. This is done at each separate LOFAR station and in each participating country. Subsequently, all the digitized signals come together at a correlator, Cobalt, in Groningen, which is a powerful supercomputer. In turn, Cobalt processes the received data. However, there is also the issue of the data being polluted. It needs to be cleaned first. So let's go back a bit. The radio waves that reach our planet are distorted when they pass through the Earth's ionosphere. This distortion is comparable to how a diver, looking from underwater at a person standing at the edge of a pool, sees that person. The rippling water surface distorts the image that the diver sees, but the diver knows that he is looking at a distorted image and the actual person looks different. But we have developed algorithms for LOFAR to correct these distortions. Another form of pollution is radio signals sent out by devices such as mobile phones and drones. These radio waves come from other directions and are much stronger than the radio waves coming from the universe. These pollution radio waves are filtered out. The data arrive at the correlator Cobalt, which processes these data in real time and sends them to a SEP cluster. Here, the data are filtered, corrected, and processed further offline. Finally, these process data are archived, and users, astronomers, can retrieve the data for further processing to, among other things, create an image.
Hi, I'm Brian Hare. I'm a researcher at Astron, the Netherlands Institute for Radio Astronomy. We are here at the LOFAR radio telescope, which I use to study lightning. Here we have a small spark generator called a Wimshurst. If I turn this crank, it will make sparks in between these two metal balls. And then over here we have a radio. If I turn it on, it'll make a little bit of static noise. And it'll actually pick up the radio waves that are being made by the sparks. This is very similar to like LOFAR, which is like a radio, but much more fancy and sophisticated, picking up radio waves being made by lightning. So now if I turn this, you can hear the static sound from the radio becoming quite a bit louder. Small sparks are like small lightning flashes. They emit lots of radio waves, which we can hear with the radio. So this is a bit of a demonstration about how LOFAR can also pick up and listen to the radio waves coming from actual lightning above LOFAR. We can use this data to image and map lightning as it gets started and grows through a thunderstorm, and even as it connects to tall structures like wind turbines and tall buildings. We do this because we really don't actually understand lightning. We don't understand how it gets started, we don't understand how it grows, or why it does any of the other weird stuff that it does. So by making images in this way with LOFAR, we can try to probe the plasma of the lightning to understand how it's working.